Let's talk about the human eye. So in human eye, we are basically interested on the part of the eye lens. Okay, so this one, so this is the eye lens. Okay, and in the eye lens, you see it is attached to the both side with the ciliary muscles. Okay, so the main role of these ciliary muscles or ciliary fibers is to change focal length, focal length of eye lens. Okay, so here, because of that, image will be formed always on the retina. Okay, so image will be formed at retina. Okay, retina. The image is always real, inverted. Okay, so the main role this optical nerve is to reinvert so that image looks erect to us. Okay, so we are talking about our eye, human eye. Okay, so in this part we are mainly concerned with this kind of functions. Okay, so this means if the object is in front of our eye, then image will be formed here. Okay, so image is at retina. Again, image will be real and inverted, and the nerve here joint, this is called the optical nerve. It will, the main role of optical nerves is to reinvert the image so that it appears again, just like I told, it appears as a erect. Okay, so in the, if our eye lens could not focus on this part in the retina, then we say that this eye is the defected eye. This is our defected eye. So in our course here, we are mainly concerned with the two kind of defect. One is the myopic eye, other is the hyper hyper eye. Okay, so this is the defective eye. In this case, you see that the rays is converged in front of retina. So the rays you see is converged in front of retina. That's why we cannot see the person having this kind of defect cannot see the object. Okay, this is defective eye. In the second scenario, you will see that the rays are these incident rays are going to be converged beyond this retina. Okay, beyond the retina. That's the reason this eye is also is the defective eye. So in our course, we'll be talking about only these two kind of effects. Okay, so we have to use lenses in front of our eye to correct those kind of defective regions. So we are using either both kind of lens. We can use concave lens and the convex lens. So this is the concave lens. Okay, so and we are also using the convex lens to get our eye free from those kind of effect, those kind of defect. Okay, so let's talk about this in some with some sketch. Okay, so Okay, so let's start again. So with the brief introduction, human eye. Okay, so I'm just drawing the rough sketch. Okay, so this is our eye, and for simplicity, I'm just making this portion is our eye lens. Okay, this is eye lens. So the rays parallel to the principal axis to our eye lens will converge to the retina after refraction. Okay, so image will be formed in the retina. So for normal eye, her point is infinity, means person can see the object at infinity. Okay, so this means person can see the object at infinity. Okay, let's draw the picture again for the eye. Okay, so again I'm drawing the same picture, similar picture like this for our eye. Okay, so this is my eye lens. This is the axis, principal axis. If the object is situated at the near point, so the rays coming from those near point after refraction from the eye lens will meet at this point in the retina. Okay, so in this case, this is the near point. Okay, so near point is roughly, it depends person to person, but it's roughly 25 centimeter from our eye. Okay, so this is for the normal eye. Okay, if there is no any kind of defect, so this means the person can see the object at near point. So up to this point, we're talking about the eye which has no defect, basically. Now, let's come to our point. Say, for example, let's talk about two kind of defective visions. Okay. First one we'll talk here is myopia, which is also called near sightedness. This means the person who has this kind of defect can see close objects clearly. Okay, but can see object at infinity clearly. Okay, so if you draw that picture, we can say that the person who has this kind of defect, say I'm drawing the ray for the eye. Let's see if the person's eye is just like this, and this is the eye lens. Okay, so the person can clearly see at the object at the near point. So if the object is situated at 25 centimeters from the eye, this rays will be focused on the retina. Okay, but the same person having this kind of defect, say the rays coming from far away, these rays will not meet at retina. Okay, so this is the object at infinity. These rays after refraction will meet in front of retina somewhere. So this person can see the object which are very far away at infinity. Okay, so this is the scenario for the person having this kind of defect. This means for this kind of person, far point is not infinity. So let's draw the picture again. Okay, so the person having this kind of defect, say, let's draw the picture for the, say, this is eye lens. So this is the retina. So the image, he cannot see the object at infinity, but he can see the object to a certain far away. Okay, so say this, he can see up to this point. Then this ray will converge at the retina. So this point up to where he can see is called the defected far point. Defected far point. So the person having this kind of defect, far point is not equal to infinity. Then we have to define the other point up to which he can see it. Okay, so the defected far point, say, let's say this will be the something, this distance, I call it x. Say that's why defected far point will be x instead of infinity. Okay, so this means is clearly to see the object at infinity, the person should use a lens so that object distance equals infinity and image distance equals this defective far point. Means we have to put the lens in front of this eye so that image will be formed at the defective far point. If the image will be formed at the defective far point, the person can see this defect. Okay, can see the object at the very far point. And in this case, let's see which kind of lens we should use. We say that we need a lens, but which kind of lens? Which? Either concave or convex. Okay. So we have to decide which lens we should use. So to understand this part, we have to understand the one thing I will write here, just it is a note. If you have a convex lens and if you pass the rays parallel to the principal axis, means it will bend towards the principal axis. Okay, it bends towards the, so this means bends towards the principal axis. Okay, if you take if you take the concave lens, then if you pass the parallel incident rays, it will bends away from the principal axis. Okay, so in this case, it bends away from the principal axis. So based on these two concepts, we can say which lens. Certainly, we cannot use, if you see that, if we are going to use here the convex lens, this point will be shifted further towards the eye lens. So that's the reason we have to use, in this case, we have to use the concave lens. Okay, so this means in this case, we should use suitable concave lens. Okay, so what I mean by suitable concave lens? So let's draw the rough picture of the eye. Okay, so this is my eyeball or eye lens, and this is my principal axis. Okay, so if I use the concave lens close to our eye, so this is, we are assuming that eye, lens, and concave lens are close, are close enough. We are assuming this. Okay, so in this scenario, if you pass the rays parallel to the principal axis, means the rays coming from this rays coming from object at infinity. So after refraction, you know that after refraction, what will happen? It bends away from principal axis little. Okay, then our eye lens actually focus on this retina. Okay, then we can see the object at infinity. So can see the object at retina. And can see the object. This means final image will be at retina. Okay, so this means if you produce rays backward, you know that, okay, they will meet at certain point. This point will be the defected far point. Defected far point for the person. So to looking for that, we can find the focal length of the lens. Okay, so based on that, you can say that for concave lens, object distance will be infinite, image distance will be from this picture, the image must be found here. So image distance is equal to the defected far point. Defected far point. If you know these two things, use the concept of the lens formula and find focal length of concave lens. Okay, we can do that. So the other defect we'll talk about here is the far sightedness. Okay, and it's also called the hyperopia. Okay, so the person having this kind of defect can see object at infinity. Means he can see the far object, but can see object at near point clearly. Okay, so if you guess like what kind of picture looks like, okay, if this is eye, I'm just talking about eye lens. In this scenario, rays coming from infinity will meet in the retina. So this means the person can see the object at infinity. Okay, let's draw the picture again. So this is my eye lens. Okay, this is my principal axis. Say object is situated at the near point. So we know that roughly near point is 25 centimeters from our eye. So the rays coming from the near point will meet beyond the retina. So in this case, the image will be in the retina. In this case, the image will be formed beyond retina. So our retina is here. So in this situation, the person cannot see the object at near point clearly. So for this person, which we are talking about, the near point is different. So if I draw the picture here, and this is for my eye lens, okay, the person having this kind of defect, the near point could be different. Say now near point should be somewhere here. So this is the defected near point. Defected near point means what? The near point is more than the roughly like 25 centimeters. So this means that rays coming from the defected near point will converge in the retina. Okay, so this is for the defected near point, the person can see clearly. So to remove this kind of defect, we know that clearly we have to use the convex lens. Okay, we have to use the convex lens. So let's say we need a lens which forms the image of an object kept at near point at defected far point. What does it mean? Okay, so this is my eye lens. In this scenario, I have to use convex. I have to use the convex lens, so that what will happen if I put my object at near point. This is near point. Okay, the rays coming from the near point, the object, because of the object here, what will happen? This rays further bends toward the principal axis and finally meet at the retina. So this convex lens will form the image somewhere. Say, for example, you know that the image will be formed here. So this will be the image position for the lens. Okay, means this image should be at the location of defected near point. Defected near point. Okay, so for this lens, for convex lens, object distance is equals to the nearly 25 centimeter, or it will be given, and image distance will be equal to the defected near point. Defected near point. Okay, if you use this concept for the lens formula, then you can find focal length. Focal length of the convex lens. Okay, this is the concept behind that. So you just so I want to repeat one more thing here, that in the case of, is just a note we have seen before, that if you have a convex lens like this, okay, our eye lens is also we have such a convex lens. So this is the principal axis. So you know that if you put the object between optical center and focus, image will be real. Image will be not real. Okay, it will be the virtual image. One ray parallel to the principal axis, it passes through focus. Other ray through the optical center will pass straight. So they will not meet. So refracted rays not meeting. Do not meet. Really. In the real sense. Okay, so we have to produce back, then image could be formed somewhere. So you see that this is the image position. Okay, we get the virtual image. We use this concept for the case of our eye. Okay, so you have seen that, you have seen here that same thing could happen for this lens. This is your object. So you should form a virtual image at this location. So this location should be exactly at the defected near point for our eye lens. Okay, so and This is for just for the purpose of note purpose we have done before. Say, let's define the power of lens. Power of a lens, okay, is equal to 1 over focal length. But focal length should be in meter. Okay. And this, the unit of power of a lens is diopter, D-I-O-P-T-E-R. Okay, diopter. So we can also write in short as D. If you understand up to this point, you can solve this problem.